Hi, AP Physics. It's time again to learn about some of Newton's laws. Now, I know that you're familiar with them in the general or in the very simple law forms that you memorized in previous physics classes, but in this video, I'm going to be going over some of the nuances that you need to know for the test and just in general for problems. So the first piece that we need to learn about is force, right? This is the main thing that Newton's talking about. It's on the screen. I am typing the two definitions. One is for force and the other is the first law of motion. So an impressed force is an action exerted upon a body in order to change its state, either of rest or uniform motion. Okay. And I write in a right line. That just means it's moving in a line, not necessarily to the right. The second one is the law of inertia, and this is maybe phrased a little bit different than you're used to, but it's going to be helpful for us. So everybody continues in its state of rest, or I meant to have that as uniform motion in a right line unless it is compelled to change. That state by force is impressed upon it. So the first thing that we should notice is that these two kinds of definitions are a little bit cyclical, right? We talk about force, which changes its state, or the object is at rest and it stays that way unless it is compelled to change, right? I've kind of flipped the two clauses here. So a simple test for this that we could perform is tossing a ball straight up in the air while driving in a car. Now, let's say this is a nice road in Texas, right? It's nice and flat. It's going in a line for miles. You could fall asleep driving it. So I'm going to be tossing a ball straight up in the air while I am the passenger. I'm not going to be driving this car. That would be dangerous. We just learned about the safety precautions we need to take while driving. So if I toss this ball as straight up as I can, you should notice, if you're the one doing this in your own car, that the ball goes straight up and comes back down. It doesn't fly forward. It doesn't fly backwards. It stays with you, right? You could do this on a train, but we don't often drive trains or on a train. Now, a passenger on the side of the road, maybe it's a farmer in Texas, right? They see us tossing this ball straight up in the air, but from their perspective, it's no longer straight up in the air. Now it's going to have some horizontal motion to it, right? It's going to be acting in two dimensions. Now, this is what we describe as an inertial reference frame. So from my perspective, from my inertial reference frame, and let's say I'm moving at that constant velocity, right? That the ball only looks like it's going straight up and down, but that's because I'm moving with the car, right? The ball and I and the car all have the same velocity. So from my perspective, it only looks like that. But from the farmer who's on the side of the road, well, they see the car moving. They see it driving along with myself and the ball moving at the same velocity. So when I toss it up in the air, it now has this classic parabolic projectile motion. So the next piece that we need to go over is about mass. Now, mass is really similar to the law of inertia, that second definition that I gave you. But mass is, and based on our textbook, says that it's the property of an object that specifies how much resistance an object exhibits to changes in its velocity. Now, let's consider the experiment that you did in Heinz' class if you took it. Right? He gave you a bowling ball to be moved by a broom. Now, if you remember back to that experiment, you should remember that it was actually quite hard to change its velocity, either to speed up or change direction, right? To get it to go around a corner or to move faster or slower in a particular direction, right? Around a corner, it was probably pretty hard, right? It was going in a straight line and you want it to turn. So you start attacking it from the perpendicular side, but then it keeps going in that line. It's really, really hard to get it to turn because it wants to keep going down the hallway. So this is what we talk about in terms of mass as a resistance to that change in velocity, right? The more mass something has, the harder it's going to be. The less mass something has, the easier it's going to be. Right? This is really easy to move a penny around a table, but it's going to be really hard to get a car or a semi-truck to begin to move or change direction. Now, notice that I don't mention anything about lightness and heaviness, right? This is because mass and weight are different, right? If something is light, I'm talking about the weight. If it's heavy, I'm talking about the weight. This is then going to bring us to our next part, which is about gravity and about weight in particular. So gravity is a force, and we are going to be writing it as F sub g, and force is a vector. So we're going to give it a vector symbol above, and it is equal to, right? We talked about Newton's second law in our lab, that it is the mass, that inertia, multiplied by the acceleration due to gravity, which is also a vector. Now, for the most part, you can use 9.8 meters per second squared. But you can also use the equivalent at times of 10 if that is going to be a little bit faster for you. So on the test, you can use the 10 if you would like, but I would recommend using the 9.8 just to make it a little bit more accurate. Now be careful when doing this, because this is what we were talking about before. So Fg is what we would consider weight. So when you stand on the scale, you are measuring your weight, but you are actually measuring the force that Earth pulls you down at. Now, if I went to the moon, right, you can immediately get lighter. The book talks about going on top of a mountain and you lose a couple of newtons. That does not mean that you lost it during the exercise to get up to the top of that mountain. You actually lost it because gravity is not pulling you nearly as hard as it was before. Okay. So one way we can remember this is by just simply reading the equation, since it kind of rhymes, right? So we can say Fg equals mg. So if you ever forget the equation, you can kind of remember that little mnemonic device, Fg equals mg. Now, know that this value for g at 9.8 meters per second only applies to the Earth. If I went to the moon, I would get a different value for g. If I went to Mars, I would also get a different value for g. It depends upon what planet or moon or sun that I am being attracted towards. So let's consider for a moment. Our friend has won a Newton of gold in a contest, and they are on the moon. Now, you say you also have won a Newton of gold. So let's consider who's got more gold, you on Earth, if you have a Newton, or your friend who is on the moon. So we can look at this in terms of an equation. So we both have the same Fg, right? We both have the same force. It is 1 Newton of gold. Now, your friend is on the moon, and we're not sure how much mass there is, but we know that the acceleration of gravity is a little bit smaller. And you live on the Earth, who have the same amount of newtons. You don't know what the mass is, but you know that your acceleration of gravity is bigger. Now, since the two masses are unknown, but we know the gravity, we can see how they are proportional. So this mass is going to have to be larger, and this mass is going to have to go down to compensate. So that means that your friend has more gold, and that means they have more mass. They got more gold. So your friend has more. So now that we have talked about the Newton's first law, we've talked a little bit about the intricacies of mass and weight. We now can move on to Newton's final law, which is his third. Now, Newton's third law can be a little bit tricky. We can think of forces having equal and opposite reactions at a lot of different places, but really it is always two objects. And so the picture that they show of two different sized objects pulling on each other is the right way to think about it, right? And I can use these congruency lines. So this is, let's say this is the first object, this is the second object. So this object is being pulled by 2, and this object over here is the second object. It's being pulled on by 1 and 2. Okay. Now notice that they are in opposite directions, right? So this is a part of it. So I can say that force 1 of 2 is equal to the negative value of 211. One way that I like to describe this law is that it is for every force, there's an equal and opposite force acting on another object. So one example that is not Newton's law is of a person standing on the ground. Okay. Now I can draw the forces off to the side acting on my person here. And right, gravity is pulling them down, so I'll call this Fg, right? That's the force of gravity. And then there's also what's called the normal force, and this is any surface that pushes against an object, and we'll write that as F sub n. Now these two forces are equal and they are opposite, but this is not Newton's third law because it is only acting on my guy here. Now, if I wanted to know what Newton's third law was happening, I would actually have to draw the Earth, okay? So there's my little tiny Earth underneath my dude. So if I wanted to know what force had an equal and opposite one on my guy, it would actually be the force of gravity that my guy pulls on the Earth. These two here, these two forces, this one and this one, that is a Newton's third law pair. These two are not. Be careful when you're looking at Newton's third law. It is two objects exerting equal and opposite forces on each other. So we could also think about this as a person pushing on a table. So where is the third law pair? Well, I would need to consider two objects. So I need the person and the table. So I'll need to draw my dot and my dot, right? Now, the person pushes on the table this way, force of the person, and the force of the table is going to push on our person backwards. These are going to be equal and opposite forces, right? The table on the person and the person on the table, right? Notice how that matches our image just up and to the left. Now, something that I've been doing all along is draw what's called free body diagrams. You can also call them force diagrams, but whenever we do this, we want to draw all the forces coming from a central point. So if I have a person, and there are several forces acting on my person, I'm going to draw a dot, and all of those forces are going to be coming from there. So, right, there's the force normal of the ground, right? And there's the force of gravity. Maybe there's a wind that's pushing me a little bit this way, right? So all of these forces are going to be coming from the central part. But this gets a little bit messy. So simply what we can do is we can draw all the forces just from a dot, and we don't even have to draw the object anymore. So we can draw the force of gravity pulling down. We can draw the force normal of the ground. And maybe that wind as well pushing me a little bit to the side. Right? So this is much cleaner, and all of my forces have been labeled. Now, before I move too much farther with free body diagrams, I also want to talk about this force normal. So just to be clear, it is a force that is applied by a surface perpendicular to that surface. So if I have a horizontal surface here and I have a box, boxes are always nice to draw force diagrams on, right? The floor is going to be pushing up on my box, right? It's perpendicular. But force normals don't always point straight up. Sometimes force normals are on an incline. Here's my box again. It's a little lumpy. Now, since the incline, well, my surface is now on an incline, essentially. It's at an angle. My force normal points out this way. And this causes some particular problems when my force of gravity still points straight down. So we will be talking about this sort of problem in more detail in class. So now that we've done Newton's third law and we've looked at some pieces of forces and mass and weight, let's do some practice. So the first thing that we're going to be looking at is a particle in equilibrium. Now, it might not be in equilibrium. We're going to be looking at example 5.4, and what it wants us to know or figure out is if this traffic light is going to have some broken cables. So the first thing that I want to do is I want to assume that, let's just say it is in equilibrium and all these cables are strong enough, because that way I can figure out what the tension is in each of them. And then I can evaluate at the end if they exceed 100 newtons in force. So we have kind of an interesting setup here. So if I know that all of my forces have to add up to 0, let's think about it in terms of the x and y directions. So the forces in the y directions, the summation of all of them, it's going to have to come to 0. And I know that's going to be tension 3 plus the first tension. And I want the vertical component, so it's going to be sine of theta 1 plus tension 2 sine of theta 2. I then also know that the summation of all the forces in the x direction is also going to have to add up to 0. So that means it's going to be negative tension 1. Since I'm going in the negative direction, I might as well just do it that way. Cosine of theta 1 plus tension 2 cosine of theta 2. Now, notice that I have a system of equations. So the first thing that the textbook does is it finds tension 2 in terms of tension 1 using the horizontal equation, giving us tension 2 equals tension 1 cosine of theta 1 over cosine of theta 2. So now we can plug this back into our original equation for the summation of forces in the vertical direction. So this is going to be T3 plus T1 sine of theta 1, right? And then the T2's got to turn into that T1 part, right? So it's T1 cosine of theta 1 over cosine of theta 2 times sine of theta 2, which is kind of nice because then we have just the inverse of tangent. So we have T3 plus T1 sine of theta 1 plus T1 cosine of theta 1 tangent of theta 2. So now we can solve for T1, right? We know everything in this equation. We know theta 1, theta 2, and T3. So let's solve for T1. We have that negative T3, right? We got to subtract that onto the other side. And then we divide by the sine of theta 1 plus cosine of theta 1 tangent of theta 2. It's getting a little scrunched in there, but I hope that's still readable. So if we plug in all our numbers, we find that the first tension is equal to 73.4 newtons. That seems to fit pretty well. And if we plug in T1 back into our equation for the forces in the horizontal direction, we can solve for T2, and T2 ends up being 97.4 newtons. Now, I wouldn't want to be engineering with that close of a number to 100, but it does mean that our cables are not going to break. So one thing I want to point out with this is that we worked with a system of equations to solve for our answer. Okay. And also be careful about this term here. They solve with it being terms of negative FG. You can also solve that way. Notice it comes out a little bit cleaner in terms of the sign, so you don't have to have negative and a negative again to get the positive. Okay. So system of equations, solve for one of our unknowns, plug it in, and then finally solve.